サススキー場です。
So for now, transition is talking specifically about how turbulence impacts the star formation problem. And I really, can't overemphasize how important star formation is in astrophysics. I think most of us realize that star formation and stars in particular touch on nearly every astrophysical problem, from planet formation to stellar evolution and element formation to energy injection into the intergalactic medium. All of these different processes are very much linked to the evolution of stars, but at the same time, we still don't have a complete theory for how stars are formed. And so this is a problem where we need to think about the dynamics of the interstellar medium. And so the interstellar medium being turbulent, and in particular being supersonically turbulent, this really has two effects on star formation. This is essentially our modern understanding of the problem. There's two effects. So on one hand, supersonic turbulence can enhance star formation, because as I was showing you in this movie, we saw these density features moving around. Right? So the density is not uniform. Right? We have a fluctuating density field. So turbulence can enhance that density field. And those density enhancements can collapse on their local free fall time. At the same time, turbulence provides the formation of shock density features can be seen here, and then corresponding the evolution of the density power, or the density PDF is on the right. So you can see that this interaction of multiple shocks that forms in these simulations produces this nice log normal density distribution. Okay, so this has been noticed in basically everyone's simulations, that when you have turbulence, you get the formation of log normal form. And then here it is. So, okay, great, this is the form of the PDF, and some turbulence, and then the item is turbulence, therefore we can write down various analytic theories of star formation based on this log normal form of the PDF. And that's been done in a number of studies. This is not even remotely an exhaustive list, but basically the initial mass function, the star formation efficiency, the star formation rate, the Schmidt relation, all of these various studies have been done that are all based on the log normal PDF. And how does that work? Well, it's actually pretty simple. Simply, you know your form of the density PDF, and you want to know some critical density over which collapse will begin, and you have some critical density, and maybe you write down some description for that, and it varies for different studies. Okay, once you have your critical density, you can just integrate over this log normal form, and then you have your total density that collapses into stars, modulating that by a free fall time, and you can then normalize everything here to have a unitless star formation rate for free fall time. And then of course, there's a fudge factor, as always, so there's an epsilon here that accounts for feedback, so now all of this gas ends up becoming star forming, so some of it gets checked out, and then maybe you have another fudge factor here for modulating this free fall time, which can also depend on different densities as they collapse. And so you can write down the star formation rate analytically then, because you know the form of the PDF is log normal. And so then you can easily write down star formation rate, which depends on the properties of the PDF, as well as that critical density that you define. So this has been tested in quite a number of papers, both numerical as well as some observational work. And essentially, I've put up here three of these more popular log normal-based star formation theories. And these were tested in a paper by Federac and Tuckman in 2012, where they took all these different theories and also even modified those theories, and then tested them against simulations, changing things like the sonic Mach number, the virial parameter, and the star formation rate. And so basically, all these theories, they all use the log normal PDF. The only real difference here is they have different prescriptions for this critical density over which collapse can happen. Okay, so there's some modulations with the Mach number, the virial parameter, and then some of these other parameters, which I won't go into, but suffice to say they all have different critical densities. There's some universal predictions, though, because they all get the same form of the PDF. So some of these predictions include higher star formation rates for free fall time with increased turbulence. Constant star formation rates if all these different turbulence parameters stay the same. Right? The star formation rate should be roughly constant given all these parameters. Lower star formation rates for higher virial parameters and negative field. Okay, so that should make sense. And then the critical density for collapse, which depends on a number of various parameters of order unit here. So you can see those predictions correspond to increasing star formation, lower.
Dr. Joaquin Vieira of the University of Illinois about aspects of star formation at high redshift. Joaquin, I've known Joaquin a long time. He is an expert on inferring the physics of galaxies at high redshift, especially star formation. It used to be true from millimeter to millimeter observations. That's where he got his start. But he's branched out. So he's got other wavelengths in his repertoire now. He's going to tell us about that today. In fact, just my personal observation, since I've known Joaquin so long, I'm going to embarrass him and just mention that I think it's fairly remarkable how in such a short time he has progressed from a prediction, which was of the just the brightness distribution and the number distribution of a certain class of objects at high redshift. He's progressed from that prediction in a very short span of years to finding candidates for those objects and then following up to confirm them. Which I personally think is a very impressive feat, and I think he's going to be talking about that today. Now I'm going to give you the resume stuff. Joaquin did his thesis at the University of Chicago with John Carlstrom. I believe the title of his thesis was Extragalactic Millimeter Wave Sources in the South Pole Telescope Survey Data, which is a rather prosaic title, if I may, for the beginnings of a campaign that Joaquin has been deeply involved in, if not led, that has changed a lot of what we think about millimeter galaxies at high redshift. So he finished his PhD in 2009 and he went on to Caltech, where he was a postdoctoral researcher with Jamie Bach, who was a recent visitor here. And he joined the faculty of the University of Illinois in 2013, where he founded and is now director of the Observational Cosmology Laboratory, which involves maybe a dozen or so undergraduates, scientific research. And he's known for other things. Among them, he's a member of the Origin Space Telescope Science and Technology Definition Team. And he remains deeply embedded in the physics of star formation at high redshift, and that's what he's going to tell us about today. And it's high redshift star formation under the cosmic microscope. Let's welcome Joaquin. Thank you for having me. Very fun. Okay, so I have a title for you on that. So high redshift, by high redshift I mean typically bigger than redshift 1 and kind of specifically redshift 2 to 7, but maybe showing beyond that. Star formation, how stars form beneath of that, how and the observables that we use to measure that. And under the cosmic microscope, this was that was one introduced by Einstein. And he this is the rules to discover these galaxies, this is actually about the wilderness as well as the smells, and from my teacher for to go.